Okay. Hi everyone. Welcome back to the second session of the computer vision workshop. My name is Chloe, and today we'll be going over generative models. So this is mostly going to be in the 2D realm of things. And so again, about me, I'm a fourth year computer science and stats double major. I previously worked as a data scientist at Manor International and research assistant at UHN working on biomedical imaging. And I'm currently researching 3D part segmentation for rare polygon shapes at the Toronto Intelligent System Labs using diffusion models. And my research interest is in 2D and 3D vision. And previously, I was also working on deep learning for genomics. And so in the previous session, we talked a little bit about supervised versus unsupervised learning. But so for today, I want to talk a little bit about a different way of classifying like task. So a different way that we can talk about this is discriminative versus generative models. And so whenever we talk about these, then we were always imagining some kind of probabilistic models or a probabilistic structure in our data that we're trying to learn from. And so in discriminative model, typically we have some label Y and the data X, which is here is a kind of image. So it's inherently has a really large and high dimensional structure. And so we would try to learn a probability distribution of Y given X, or like conditioned on our input image X. And so one very important feature of probability distribution is the idea that it's is normalized. And so when we have a, this is called like a density function, which it will just try to assign a positive number to every possible input X. You'll have like a higher number if it is like more likely, and lower or close to zero if it's otherwise. And so the idea of normalized is that if you integrate over the entire space of all possible X's, then it will integrate to one. And so what happens is that, so for discriminative models, there's only a fixed amount of probability mass that there can be. And so inherently, if you have like, if you have this picture here, and then you're trying to assign the probability of it being a cat, then if you assign it to be higher, then then inherently the probability of it being a dog has to be lower because it's all sum up to one. And so the idea is that for this, then for each image, we have a distribution of itself. And then if you give it like another image, then it'll have like another set of distribution on its own. And so the key idea here to remember is that these images aren't competing against each other, like they're existing, different, separate from its own. And so a problem with this is that the discriminative models are rather not flexible. Say if we define in the very beginning, if we define that there can only be class cat or class dog, then later on, if you fit it like a random image of a monkey, it will still try its best to assign, to cat or dog, because that's all it will ever know. So it's just constrained in that. And so it doesn't know how to handle unreasonable inputs. And so it will try to give a label distribution for all possible inputs. And so you can kind of see that it's a huge shortcomings in terms of image understanding. And so this is where generative model comes in. So in this case, all images are competing against each other into like this distribution of labels. And so this is interesting because it will try to learn from all the images possible out there. And so this requires our model to have a rather deep and innate intuition of the world, as well as like just as good as a human could do. And so it'll have to be able to get, like a really deep understanding of the world. So say, for example, if we set our context to be all possible animals in a zoo, right? And so if we give it two images of like, like a three-legged dog versus like a three-eyed raven, then the question becomes like, like it will need to be able to somehow learn that yes, a three-legged dog is more likely to exist, even though it's not, it's different from like a normal dog, but then it's high more possible than a raven because like it's more likely that it may be like it blows a dog, lose like a leg from like an accident versus here then like this is very less likely to exist in real life and it is more like a mythical creature, which it is, by the way. That I took this from Game of Thrones. And so yeah, and so another thing that is more exciting about this is that this model will have the ability to basically say no, because when it's assigned with this context and given the three-eyed raven, then it should be able to assign a really low probability and close to zero, and saying that no, like this is not a reasonable image. And so another thing that we can think about is that for a if we move up like another step, which is conditional generative model, is if we give a condition of something that is much more nuanced and richer than just a categorical label of like cat or dog. If we give it like an actual sentence, and then we give like a text description or a whole paragraph of written text, then we want it to like say like instead of saying we want to predict not just a given dog, but like given like a dog running on a field on like a Saturday, for instance, then so now the model will have to um, learn very rich output space X conditioned on a very rich input space Y. And so now the problems, it becomes more complicated and ill-defined, and it will need deeper reasoning about the objects involved. And so like, for example, so we can kind of see like the examples of these in like very recent use cases. So for example, conditional image synthesis. We're given like a description of, painting of a fox sitting in a field at sunrise in the style of Claude Monet. And then we wanted to learn and kind of synthesize, generate an image based on all of the representation that is learned from all the images before. And so with that in mind, then we want to I'm just gonna kind of slightly go over the like probabilistic modeling underneath all of these. And so even though we talk about these models are like different, they're all related to each other through Bayes' rule, which is a cornerstone formula in probability. And so say if we have access to a discriminative model here, and then we have an unconditional model P of X, as well as some prior distribution over our label P of Y, then we can compose these to build a conditional generative model, which is predicting X given Y. And the reason that this is really important is that we can always find one given the other two. So we can always rearrange these to find any of the other two models. And so I want to kind of go over the taxonomy of generative models. And so there are like a few big classes of them out there. So so in general, we have that generative models aim to learn a distribution of P of Y, P of X, or like if it's given a bit more specific, it should be P of X and given Y, but usually in annotation, people drop the given Y for simplicity. And so we split it into two major branches. We have models that can learn and produce explicit density, which is here. And so for any input, we can evaluate how likely a single data point is, and then we have direct access to the probability distribution. And then the other family of models is that it doesn't compute P of X directly, but you can sample from it and generate new output. And so instead of like generating like direct numbers, then they will just simply learn to sample from the distribution. And then it will capture the representation of it through implicitly through sampling behavior. And so if we go a little bit onto like this left side of things here, and so we have two subtypes of it. The first one is that tractable density type of family of models, where we can compute the exact probability of P of X. So an example of this that we'll be going over is autoregressive models. And so the key idea here is that we'll be breaking P of X into a product of conditional probabilities of all of the previous ones that it has seen before. And then another type of it is that it will try to approximate P of X instead of computing it directly. And so an example of this is variational autoencoder. And so if you go onto like the right side of like this family where we're doing implicit density, then we will have this one, which is we will directly sample from P of X. And an example of this is generative adversarial networks. And so the idea is that we will try to map all of the noise into the data directly. And lastly, we have indirect sampling, which essentially it will try to sample a new image from a particular multi-step process to generate these samples. And so an important detail of this is that technically speaking, to achieve like a perfect sample, then you would need like infinite steps until it reach convergence. But in practice, and we will usually approximate it with a finite number of steps. So first off, I'll be going over autoregressive model. And so autoregressive model is a foundational and like an early class where it will essentially, this is mostly used in text and not really in images. So we try to predict next element in a sequence based on all or a subsample of previously observed elements. And so this is the kind of the cornerstone of early image generation models. So in 2016, Google DeepMind released two papers, which is Pixel RNN and Pixel CNN. And so again, like it's coming back a little bit into like, this is like not crazy math, it's just like relatively simple. And so if we break down X into like a sequence, say we have X1, X2 to XT, then we'll try to decompose it into decompose a joint probability distribution over a sequence of product of conditional probabilities. So for example, if we want to model P of X, then it will be equal to the first one, which is P of just X1. It doesn't have anything before it. L times of P of X2 given X1. And then because that's the only thing that it has before, and then we'll have P of X of 3 given X1 and X2, and then it will go on until the very last one. And then each of these can be further broken down to this smaller probabilities given the base rules that we saw before. And so when we think about this in terms of images, then given a sequence, well, say if we have an image and we break it down into 8-bit subpixel values. So recall that in like a color image, we have 3 channels, red, green, and blue. And so we break it down into each pixel will be represented by 3 values. And the autoregressive model will predict each subpixel to classify it amongst 256 values, which is from 0 to 255. And then we can model these using either a recurrent neural network or a transformers. And so in a recurrent neural network, essentially we encode each of these into a hidden state that essentially summarize the previous sequence. And then we use these to predict the probability of the next sequence. And in transformers, then this is usually used for language modeling. So by masking out the attention matrix here, then we can make the output of the transformers depend on only the prefix of the sequence. So autoregressive models are particularly powerful for text because it's good for sequence generation with high fidelity. It's easy to interpret. It's pretty intuitive. You predict the next one given all the previous ones. And so it's good for next token prediction task, but not particularly well on images, simply because of issues of scalability. So if you have an image, for example, a 1024 by 1024, it is not like a particularly that big of an image or like that high dimension, but these already give us almost 1 million pixels. And given that each of these pixels needs 3 values, then we will need times 3. We have almost or more than 3 million subpixels. And so that means that we will have to do like the generation step 3 million times just to generate a new image. And another problem with this is that we can't do, it's really hard to scale to higher resolution, and you can't do batch outputs with this. Like imagine you have to generate each and every bits of one image, and then you can only finish that, and then you move on to the next image, and so it's really slow. Yeah, so in order to solve this, then people start to move on to other techniques. And so the next one that we will be going over is variational autoencoder. And so for VAEs, then we try to compress data into a latent, or latent essentially just means hidden representation. And then we'll try to reconstruct it into new and similar data samples. And so this technique was first introduced by Kingma and Welling in 2013, where essentially this is like a simple representation of the type of models that they're trying to go for. And where the variational parameters, phi, are learned jointly with the generative model parameters, theta. And so again, it's relatively simple. We have the input, we encode it into the latent space, and then we train a decoder to map it out into a new output. And then we try to, and then the loss will be how well it's sitting in with the distribution of the original input training samples. And so we talk about it a little bit in terms of like the math side of things. Then in a decoder network, we have the input latent code of Z, and then we have an output distribution over theta x. And so we're trying to learn P theta of x given Z. So this is the decoder. And then in terms of the encoder, then again, we have the x, and then we're trying to encode it into the latent space Z. And so the idea is that we try to jointly train both the encoder and decoder. And this is kind of like the math side of things, where we can approximate P of theta given x, which will be using against Bayes rules to get to this equation. And so during training, then we will try to maximize the log of P of theta of x given Z. which is essentially to trying to minimize the L2 loss distance between X and the network output. And so to go a little bit into the training process, so when we run input data through the encoder to get a distribution of the data over Z, and then we will have two loss that we're trying to do here. Oh, so the first one is the prior loss, or in this case, it's sometimes also referred to as KL divergence loss, where the encoder output will be of a unit Gaussian distribution with zero mean and unit variance, which is like so like this part over here. And then we sample the Z from the encoder output using a thing called reparametrization. And then after that, we run the Z through the decoder to get the predicted data mean. And then we enforce this using reconstruction loss and hoping that we're trying to enforce that the predicted mean should match the X in the L2. And so the reason why we try to use these two loss terms is because for the reconstruction loss, then again, as the name suggests, we want to make sure that the decoder can accurately reconstruct the input. And then the prior loss is to encourage the latent distribution to be as close to a standard normal distribution as possible. And so this will make the sampling possible. And so another thing to notice that this is, we're making a pretty big assumption that the distribution will be like a unit Gaussian distribution. And so like overall, like this whole term is called, the idea is to train by maximizing the variational lower bound, or ELBO. And so this is, you can kind of see that like it is really pretty math heavy. And so going over it would take like a whole session, but if you have time, then I think it would be nice to kind of like go and read about the ELBO proof on your own. It's pretty math heavy, but it's good to kind of build like an intuition of how it works. But it's really, really, really long. Okay, so if you recall, so the first two that we just have so far is we have the autoregressive models, which is using again like this probabilistic base rules, the conditional joint distribution, and then we have the variational autoencoders, which rely on the latent Z and maximizing a lower bound to determine the next one. And so these are like on the left side, the left branch of all the families of the models. But now we move on to the right side of the branch, which just gives up on modeling the P of X directly. So it doesn't want to learn from it anymore, but it just want to use that P of X and just draw samples from it directly. So, so the setup of it is this. So we're given data X of I, and we drawn from a distribution P data of X. And we simply want to sample from this P data. And so again, we will use a latent variable Z, and then we assume that it will have a simple prior distribution, which is like, say, for example, if it's a unit Gaussian again. And then we sample Z from P's of Z, and then we pass it to a generator network. And we denote this, usually denoted with a G. And then, and so we would want the sample from the generator distribution to be close to the actual true distribution of P of data. So we essentially are taking a sample of it. So and so there are two, and so like the first part of it is that we train this generator network G to convert Z into the quote unquote fake data sampled from P of G, and then we get like a generated image. And then the second part, which I think is really interesting, is that we have a separate network, which is called a discriminator network. And so this network will try to classify these generated images as either real or fake. And so the idea is that like this discriminator network, it's just there to help guide the generator network. During testing and inference, this will not be used. It just works as a guidance. And so the idea is that we're training both of these models. So we want the generator network to do very well at creating synthetic data. And then we want this discriminator network to be really good at discriminating between fake and real. And then as this network gets like more efficient, this should also get more efficient. And so again, like so like I said, we will be trying to jointly train the generator G and then a discriminator D in a minimax game. And so in the beginning, if you imagine like when a generator network is not doing very well, then the generated image will be relatively bad. And so when we compare that generated image to like a real image, then the discriminator network will be say it's like a simple binary classification of like which one is fake and which one is real. So in the beginning, these will be like the discriminator network will be really good because it is just bad because we haven't trained it before. But then what it does is that it will give really large signals towards the generator network and to say that like, hey, you're doing very, very bad, like do better, right? And so as it goes on, the generated image will start to get really similar to the real image. And then the discriminator will be slowly giving smaller and smaller signals. And so this will not only help guide the generator network towards better synthesis, but it will also give a bit more stable training. Yeah, and so again, this is just a bit more of like how this thing works. The discriminator wants d of x equals 1 for real data, and then we want it to be d of x equals 0 for fake data. So it's like it's a really simple, and I think it's a really elegant idea of training these models. And so but so again, these two models are trained in parallel. And so as we doing the training for the discriminator, we will update the gradient, which is like how much it's updating the weights with like the learning rate, the alpha values. And then for the generator, then we will also be updating the gradient updates so that it moves towards better synthesis. And so when it was first released, then GAN were mostly based on using neural networks. So as you can see here, that is usually using convolutional neural networks for both the G and the D networks. But then it starts to kind of fall out of favor until vision transformers becomes popular. And then they use the transformers instead of the convolutional network blocks to for the G and the D networks. And so I guess like another step moving up from it is style GAN, which is like it uses slightly more complex architecture. Um, and so as the generative model is learning, it will try to inject a bit of noise through adaptive normalization. And so this is still kind of depending on convolutional neural networks, but at each layer, it will predict a scale W and a shift B. And so this will be like noise that still follows Gaussian distribution injects into here. And so it will give the model even stronger generation capability, because now it will learn to not only generate from the existing sample, but also samples with noise. And so overall, just to kind of like a summary of all of the generative adversarial networks so far, then we have a generator and then a discriminator. These two try to compete against each other until the generator network achieve the desired performance. And so some of the pros of the GAN's network is that it has a simple formulation. The idea is really elegant, and the image quality is very nice. But however, there are no particular loss curve for us to check. The training with this like idea is still relatively unstable, and it's still hard to scale to bigger models and data, because like before vision transformer just using convolutional neural networks, it's still hard to scale up. And so these were okay to use from like 2016 to 2021. And then in 2021, a new contender comes in, and that is diffusion model. And so for diffusion models, then the intuition is that we start from noise. So if you recall, like from the previous methods, we often start from the true image. But for this one, we're starting from complete noise. And the noise is usually, again, in the form of like a unique Gaussian distribution. And then, and so we will consider it like corrupted data. And then we will try to go from here and then coming back and then quote unquote uncorrupted until it gets to like an original image of no noise. And so, okay, so just to clarify a little bit, so when I say that we start with noise, like we don't just get given noise. So we, given like an original image, we add a lot of noise to it to give it like this image. And then we want the model to try to recover from here, going back to the original image. And so we try to train it so that it will try to remove a little bit of noise at every step until it reaches t equals 0. And so during training, and then during inference, we will sample x of 1 from noise, and then we will apply the neural network many times in sequence to generate a noiseless samples x of 0. So there is no, so it's just one model learning it, and there's no minimax game, no generator, no discriminator, just one model. And so ever since the diffusion model came out, I think this was, I'm not sure when this came out, but about, I think, 2021. And then there's it's a really exciting idea that there have been many improvements that built up on the original diffusion models. So in particular, a really popular technique is rectified flow, which reframes diffusion as like learning a velocity field that directly transport the noise into the data and using like a simpler path. So instead of just giving it random, randomness, then we want the instead of just wandering path until it recovers the original image, which can take a really long time, then rectified flow makes it more linear. So it will be more deterministic and it will have fewer steps. And essentially the models will be both during training and inference will be faster. And so going from rectified flow, people will start to ask the next question, which is conditional rectified flow. So the idea is that what do we want to enforce a condition? How much can we emphasize like the condition of Y, as in if we want to like another big thing with generative models is that we want to be able to enforce condition. So recall back from the beginning, we don't want it to just generate like a random image. We want it to generate, say, like a particular like dog image, right? And so that is the idea of like how much emphasis we can put in the conditioning during training, and also during sampling as well. And so like the idea is that, and then like during the implementation, they just added like the Y here as a condition during each of the steps. And so these are really simple improvements, but it leads to more freedom during for like usage. And then the next step that builds up on it is classifier-free guidance. So for classifier-free guidance, it poses a question of, well, like how much, like another way for it to control the conditioning is that we will randomly drop the condition Y during training, and they will force the model to learn more and less reliance on the condition. Another very significant improvements on the original diffusion models is noise scheduling. And so during noise scheduling, then there might be many pairs of image X and latent Z that might give the same X of T. And so we want the network to be able to average over them. And so we don't want to give equal weight to all of the noise, because like in reality, then images, the noises are different. And so when we use in non-uniform noise schedules, then we will have full noise, which is a T of 1, is just relatively easy. And then we might have no noise, which is the optimal V, is the mean of P of noise. And then lastly, there's still diffusion transformers, but I want to kind of go a bit into latent diffusion models. And so for this one in particular, then instead of asking the model to learn from the image pixels, then we don't want to do the diffusion step of like adding noise. So originally, if you go back to like this one, then the noise is added to the pixels. And so we started with this really noisy looking image, and then we try to recover it. But for latent diffusion, then it doesn't add the noise to the pixels itself, but it will first try to encode the image into a latent distribution, and then we will add the noise to that latent representation. And then we will do the noise scheduling and then the recovering process in the latent representation instead of the pixels. And so in order to do this, then we'll simply use an autoencoder to compress the images. And then we'll just run the diffusion on the latent inside of the image. And then afterwards, run the decoder to get the image. And then finally, for the latest improvements is the using diffusion transformers. And so diffusion originally it uses standard transformers block, but then we want to be able to inject the conditioning, which is the time step t, and maybe like the text the conditioning into it. And so we want to replace this. So first off, so the idea is that we want to inject these condition into the transformer blocks during training. So first off, we will break these in we break again images into like patches. So using like vision transformers, for example, like a 16 by 16 patches. And then during token embeddings, each tokens will have not just the patch embeddings, but also the time and the condition. And then during the transformer blocks, where we have self-attention and cross-attention here, then it will learn from not just the patches, but also the conditioning here as well. And so hopefully by the end of the step 4 of the output, then it'll be able to predict the noise for each patch and then reconstruct the latent distribution and then the image. And then a final improvement, which is like, you can kind of see how recent these developments are because like these are diffusion distillation was in 2024, and then Nourish 2025. So it's very recent. So is the idea of using diffusion distillation. So distillation in general is a technique used not just for images, but just in for language modeling as well. So the idea is that we distill knowledge using a smaller model. And so hopefully the smaller model will be able to perform faster and still give a relatively good results as the original model. And so when we apply that idea into a image diffusion, then during sampling, we need to run the diffusion models many times. So this is rather slow. So instead, we will train a student model to mimic a multi-step teacher. And the student will generate samples in fewer steps than the original teacher model. So say, for example, technically you need like 100 steps of removing the noise to get to the original image. We train the student model to generate it skip 2 steps at a time. So it will only need to do 50 steps. But then for each of those steps, we compare between the output of the students, compare that to the teacher, and we train it such that the output is still relatively as good as the teacher. And so the students learn to jump ahead in the denoising process, so it will allow for faster sampling. And then if we can sometimes reduce it all the way to like just 1 step, then that's just like spectacular. We don't have to do so many steps anymore. And yeah, and so that is the latest improvement on diffusion models for image generation. And so this opens up to there's still a lot more methods that are still being developed to improve the process of image generation, both in terms of quality and in terms of speed and scalability as well. And so, yeah, and so I think that's it. I hope this inspires more interest in the field, and hopefully one day you guys can also contribute to the process of giving really realistic images. Thank you.